Welcome to this lecture, and this lecture is continuation of the last lecture where we understood how we can design or we can fabricate an interdigitated electrodes in an SU8 well. The reason of designing that particular sensor was to give you an idea of how we can fabricate a MOSFET, right. So, the point was that if I want to fabricate a MOSFET, then what is the technique, what are the process flow. So, to understand that technique, to understand that process flow, I have to understand initially a simple example which was discussed in our last class, and that is nothing but my interdigitated electrodes, which was nothing but my interdigitated electrodes. Now, in this class, let us see how we can design another sensor and how we can implement it using the same process flow which we have seen in the last class. Alright. So, let us see, the topic is the if you can see the screen, process to understand fabrication of integrated circuits. But this time we will take another example, so that you guys understand how we can fabricate finally a MOSFET. That is our one line goal, to understand how we can fabricate a MOSFET, alright. So, to see this, we are doing all this exercise, So, last class we have seen this, right, which is our interdigitated electrodes within an SU8 well. So, let me quickly repeat what we have seen and how we can fabricate. I will continuously show the process flow. So, be with me, alright. For designing this particular pattern, what we have done, we took a silicon, then we have grown thin layer of silicon dioxide, right. Then on this thin layer of silicon dioxide we deposit a metal. I told you which one, chrome, thin layer of chrome, over which gold, SiO2, right. We have SiO2, then we spin coated photoresist, then we did pre-bake at 90 degree. This was positive photoresist, 90 degree for 1 minute on hot plate, right. Then after doing that, we have we expose this photoresist, by placing a mask, So, we have this chrome gold, we have photoresist, and then we placed or load the mask on the wafer. The mask was similar to what I am drawing, almost similar. And then I have exposed this using UV light, After doing that, I have developed it, unload the mask, develop photoresist, right. So, I got a wafer, oxidized wafer, with photoresist, right, with photoresist. Because I am using bright field mask, this is bright field mask, right, and I have used positive photoresist. That means I will retain the similar pattern that I had on the mask on the wafer, correct. So, now I have got a positive photoresist on the area which were not exposed in UV, right. So, all the bright area on the mask I can retain on the photoresist. After that, what I have done? I have etched this wafer, this metal, chrome gold, etched first in gold etchant and second in chrome etchant. In between I have rinsed it with the help of DI water. I have rinsed it with DI. Once I do that, what I got? I got a wafer with metal on the area where photoresist was there, and rest of the area the metal got etched, right. Now, I have dipped this wafer, dipped this wafer in acetone, and it will strip, this acetone will strip my photoresist. So, when my acetone strips, or when the acetone strip the photoresist, what I will have? I will have an oxidized silicon wafer, with interdigitated electrodes, right. So, these are my chrome gold, these are nothing my interdigitated electrodes, this is my SiO2, this is silicon, this is SiO2. So, you got the process. Let us repeat once again quickly. Silicon, first step, silicon dioxide grown, second step, chrome gold deposit, third step, deposit of spin coat of photoresist, fourth step. After that, we have to load the mask. Before that, after spin coating the photoresist, you have to pre-bake at 90 degree for 1 minute. After that, you load the mask, do the UV lithography, and then you develop your photoresist. Then after developing photoresist, you can go for post bake. After developing photoresist, you go for post bake at 120 degree for 1 minute, right. Then you have the photoresist on the metal. Now, wherever the photoresist is there, the metal below it is saved, and wherever photoresist is not there, like in this area, the metal will get etched. Now, we have chrome and gold. Gold is on the top of chrome. So, first we will etch the gold, and that is why we will dip this wafer in gold etchant, which is 1. Then we will rinse it with DI. We will then etch the wafer with chrome, again rinse it with DI, and then we get the wafer which you can see here. The photoresist is there, and the metal below photoresist is saved. The metal which is not covered by photoresist got etched. After this, we have removed the photoresist by dipping the wafer in acetone, and when you dip the wafer in acetone, the PR will be stripped, and then we will have a oxidized silicon wafer with interdigitated electrodes. Now, once you have this oxidized silicon wafer, with an interdigitated electrodes, or let us just draw in the next slide. So, once I have the interdigitated electrodes, then what is my goal? My goal is to have this interdigitated electrodes inside the SU8 well, right. My goal is to form a SU8 well. So, what did I perform last time? What did I do on this interdigitated electrodes? I have spin coated photoresist, which is my SU8. So, this is my SU8. I said photoresist because SU8 works like a negative photoresist. This is my silicon dioxide, this is my silicon, this is silicon dioxide. These are chrome gold interdigitated electrodes. Easy. Now, SU8 is negative photoresist. So, what is the next step? Next step is that I will load a mask. So, after SU8 is there, I had to pre-bake it, right. Pre-bake. In SU8 we have to pre-bake it at 65 degree centigrade. Then we load the mask such that I have to create the well. So, this is my bright field mask, right. This is my bright field mask, and you have seen what is bright field mask, you have seen what is dark field mask, correct. Now, you have this. So, this is a mask, and then I will expose my wafer, with UV light. On exposing the wafer with UV light, what will happen? The area here, it is negative photoresist, which is opposite to positive photoresist. That means, the area which are exposed, will be strong, and the area which are not exposed will be weak. So, the area which is dark shaded, this area, this one, they will be weak, these areas would be weak, and the areas which are not exposed will be strong. Okay, easy. Now we have to post bake it. This is little bit different than our other photoresist at 95 degree centigrade, right. Again the time is given depending on the thickness of the photoresist of SU8. The time for pre-baking time will be different, time for post baking would be different. This is not anymore 1 minute like we have seen in positive photoresist, alright. After this what we will get? After post baking I will develop it, DEVELOP, develop the wafer in the SU8 developer, SU8, develop SU8. When I do that, what I will get? I will get an oxidized silicon wafer with electrodes and SU8. And SU8. So, this is my SU8, this is silicon dioxide, this is silicon dioxide, this is silicon, right, and this is my well, this is my well, right. So, this is how I can create an interdigitated electrodes within SU8 well, within SU8 well. Easy, right. Now see, I have continuously told you from shown you the process, I have continuously shown you the process so that you do not get lost. We have started with silicon, and then we reached to oxidized silicon substrate, which is by growing the oxide, and then we have deposited chrome gold, and on chrome gold we have deposited spin coated photoresist. After the spin coating photoresist, then we have, after spin coating photoresist we have pre-bake it for 90 degree for 1 minute on hot plate, and then we have loaded the bright field mask. Bright field mask is a pattern like this, and then we have exposed it using UV. After exposing it with the UV, we have post bake it, after exposing with UV we have developed it, develop what? Develop photoresist, and the photoresist which were exposed, because this is positive photoresist, the photoresist which is exposed will be etched, the photoresist which is not exposed will remain, alright. So, after developing photoresist I will have pattern like this, and this you can see there is a metal, then there is a photoresist, there is a metal, and then there is a photoresist, and there is a metal, there is a photoresist, and then you have metal below it, and then what you do? You have to etch the gold, then you have to etch the chrome, and you rinse the DI. In between you have to rinse with DI. Once you do that, you will have photoresist on the metal saved, that is a metal below the photoresist will be saved, and the metal which was not covered by photoresist will get etched. After this you place the wafer in acetone, and you can remove the photoresist, to obtain the interdigitated electrodes made from chrome gold. Once you have interdigitated electrodes made from chrome and gold, here chrome and gold, then you spin coat SU8, SU8 is nothing but your negative photoresist, and after spin coating SU8 you pre-bake the SU8 at 65 degree centigrade. After pre-baking SU8 at 65 degree centigrade, you can load the mask. Here you have to create the window, here you have to create the well, right, which should look similar to this. So, that is why we have a bright field mask, we have this one is your bright field mask, and you can see that the exposed area, I will expose with UV, the exposed area, that means this area, this one and this one, the exposed area will get stronger and the unexposed area will get weaker. This is the exactly opposite of your positive PR, positive photoresist, this is exactly opposite of the positive photoresist. So, now we have So, what we have done? We have pre-baked it, then we have exposed it, then we have post bake it. After post baking, we have developed the photoresist, using SU8 developer, and then once you develop the SU8, you will have a wafer with your interdigitated electrodes inside the SU8 well, So, by doing this, what we will get? We will get this pattern which you can see here, right, this one, and if you take the microscope image, then you will have interdigitated electrodes. Here your mask was such that your width was 10 micron and your spacing was 10 micron. Here the mask is such that your width is 10 micron and your spacing is 30 microns. Okay. And then this is your SU8 well, you can see this is a SU8 well, and you can see green color is your oxidized silicon wafer, Now, once you have this, if I give you another example, and quickly let us see, if I want to understand the process flow for designing a gas sensor. Now, why I am taking this example again, so that you are confident of how you can use the process flow for developing or for designing the MOSFET, right. We will see, and you will understand why we have taken this example, right. This is an example. So, when we are already making a sensor, let us also understand what is this, what is the use of this particular sensor, right. So, we are designing now a gas sensor with a process flow that will help us to understand how can we fabricate MOSFET, alright. So, let us understand first gas sensor, how can we fabricate gas sensor. Okay. If that is the case, let us see what are gas sensors. Gas sensors or gas sensor is a device which exposed to gas species, which on exposure to gaseous species or molecules alters one or more of its physical properties, that is either it will change its mass or it will change the electrical conductivity and dielectric properties. That is possible way to measure and quantify, that is possible to measure and quantify. So, here if you see, this is nothing but an interdigitated electrodes on which there is some sensitive element. What is sensitive element? That is sensitive to particular gas. So, now what you have is an interdigitated electrodes on which this some nanowires or nanostructures are formed, alright, and this is oxidized silicon wafer, right. So, the semiconductor metal oxide such as zinc oxide, MgO, CaO, TiO2, WO3, what is this? Zinc oxide, magnesium oxide, right, calcium oxide, tin oxide, tungsten oxide, tin oxide is here, sorry, titanium oxide or titanium dioxide, tungsten oxide, tin oxide, etc. are used to detect gases, and many more, alright. And we have, if you want to grow nanostructure, the nanostructure are advantage because of their higher surface to volume ratio. We do not care about this one, we just see that how we can design this gas sensor, alright. So, again we will use the MEMS technology, that is why I have given a slide, so that you understand what exactly is the MEMS technology. We have discussed in last slide that MEMS is nothing but micro electromechanical systems that in most general form can be defined as miniaturized mechanical and electromechanical elements such as devices and structures which are made using microfabrication techniques, alright. So, MEMS are miniaturized structures such as sensors, actuators, microelectronics. In the case of microsensors, the device typically covers a measured mechanical signal into a electrical signal. However, why we use this for gas sensor? If you just want to know that metal oxide operates at high operating temperature. To solve this problem, researchers have fabricated microsensor with microheater on silicon substrate. Microheaters were fabricated on IC compatible MEMS platform to reduce the power consumption. So, if generally you see that metal oxides that we have seen in last slide, they all operate at very high temperature, but if that very high temperature requires high power, I want to reduce the power. How can I reduce the power? By using a substrate which is thin. So, if I have this substrate and if I have another substrate which is thin, then the power required to hit this substrate, compared to this substrate will be less. So, power required for substrate 1 will be less than power required to substrate 2. So, how can I reduce the thickness of this substrate? I had to do machining, MACHINING, okay, machining, MACHINING. So, but in this case we have to make the thickness in terms of microns, that is why this is called micro machining, MACHINING, micro machining, okay, micro machining. So, the point is that is why we have to use the MEMS in gas sensors. Again, do we care? No, absolutely not. We do not care why MEMS is used in gas sensor, we do not care. What we care is how can we fabricate the gas sensor or how can we fabricate the sensor. Why we care? So, that once we know how we fabricate, once you understand process, you need to use this process to understand MOSFET. One line goal. How can I understand process of MOSFET? That is why we are taking different examples, so that when I come to the MOSFET, your life would be very easy, it will be extremely easy. Okay. So, let us see the process flow for MEMS sensor. So, what is it? First is you have a double side polished silicon. We have seen a silicon wafer which are single side polished. We can also have silicon wafer which are double side polished. Now, you grow 1 micron silicon dioxide, you can see here green color is your SiO2, alright. Then you have 600 nanometer of aluminum deposition on the bottom, and you can open the window, right. How you will do that? I will do that, we will see. Then you have the pattern for heater. Finally, what you want is this structure. What is this structure? We will see here, let us see. What I want is, I want a substrate, right. You guys tell me or think which substrate will require less power if there is a heater, on the substrate. So, let us say that this one is your heater, Which substrate will require less power? Obviously, right, this substrate, correct, because the thickness is extremely small. You can see this is not, this is all empty, only thickness is of this particular wafer. Here the thickness is very high, it is a thick wafer. So, in this case the power required, let us say this is 2, this is 1, the power required for 1 will be higher than power required for 2. Now, on this heater, why we require heater? Because in case of sensor we say that we have to heat the sensor at high temperature from 300 degree centigrade to 500 degree centigrade. Why? Because we are using metal oxide, we are using metal oxide semiconductor, we are using metal oxide is semiconductor, alright. So, this particular material requires a temperature of 300 to 500 degree centigrade. Now what? Now what is the case? Once you have heater, you need a sensing material. So, on this heater, let us say because it is bigger, I have to have an insulator, right. I have to have an insulating material, let us say this is SiO2. On this insulating material, I can have my interdigitated electrodes. What will I have? I will have interdigitated electrodes. On this interdigitated electrodes, I want to have my sensing material. I want to have my sensing material, correct. This is my sensor, but instead of using this, I will use this substrate, I will use this substrate, I will use an insulator, I will have my interdigitated electrodes, right, and I will have my sensing material. Advantage is the thickness here is less, correct. So, to obtain this particular sensor, to obtain or to fabricate this particular sensor, what is the process flow? What are the process flows, right? You understand this, you have to remember. What we want is this structure, want to have this structure, alright. So, first is, now you see, if I use silicon wafer, right, then I grow oxide, okay. I have silicon, I am growing oxide, right. Then I am depositing aluminum on the back, and I am etching the aluminum, this is aluminum or metal, and I am etching the metal using process which is our lithography. What we do? We spin coat photoresist. So, I will spin coat photoresist, right. Then after spin coating we pre-bake it, So, I will pre-bake it at 90 degree, this is my photoresist, positive photoresist. After pre-baking I will load the mask, which kind of mask? I will load the mask like this. Alright, I will load the mask. Now, after loading the mask, what I will do? I will expose this wafer with UV light, expose this wafer with UV light, alright. So, what will happen? That after I unload the mask, if I do this, after I unload the mask and I develop my wafer, I unload the mask and I develop my photoresist, then what I will have? I will have oxidized wafer like this, and I will have I will have metal and photoresist. Once I unload the mask, right, this is, see what I have done, silicon dioxide oxidize, then I have deposit metal, on metal I have for photoresist, I have pre baked it at 90 degree, then I have load the mask, I have exposed the mask, then I have developed, I am unloading the mask, I am developing photoresist. After developing photoresist, I will have this particular structure because this is my positive photoresist. So, the same structure I can retain, right, or the exposed area is weaker and unexposed area is stronger. So, I am retaining this particular structure. After this this is what my photoresist, right, my photoresist, this is my SiO2, this is silicon, this is SiO2, right. What I want this structure, all right. You remember what I want. Now, let me remove it. So that you can see what are the process flows. So, this is my another one. Now, I will dip this wafer, in metal. So, after this what is the next step? After this we will do post baking at 120 degree for 1 minute, right. After this, after post baking, I will etch my metal. So, when I etch my metal, what structure will I have? I will have structure which will look like this, right. This is metal, this is PR photoresist, this is my SiO2, this is silicon, this is SiO2. You see difference, here the metal was here in this one, here this metal is not there because I have after post baking I have etched the metal, all right. So, after this what I will do? I will etch SiO2, I will etch SiO2. So, for etching SiO2 I can dip this wafer, in buffer hydrofluoric acid, I can dip this wafer in BHF, okay. BHF, why? Because BHF is SiO2 etchant, all right. So, I can dip this wafer in BHF. If I dip this wafer in BHF, what will I have? I can I will have SiO2 only in this place, because this is covered by, this is protected by photoresist, then I have photoresist, metal and SiO2, easy, very easy, right. Now, I will strip off my photoresist, I will remove my photoresist, I will strip off my photoresist. Okay. Now, I will deposit a metal on the top of the wafer, and this metal is my metal for heater, Then I will spin coat photoresist, this is my positive photoresist. After spin coating photoresist, we will pre-bake it, 90 degree 1 minute. After pre-baking, after pre baking I will expose the photoresist using a mask, and you will see how useful this process is when we look at the MOSFET fabrication. Okay, guys. So, please focus what we are using, a bright field mask, we have here photoresist positive, we have here SiO2 and I am exposing with UV, I am exposing with UV. When I expose it with UV, I have to, after exposure I will unload this mask, right, I will unload this mask and I will dip this mask in photoresist developer. When I dip this mask in photoresist developer, what will I have? I will have photoresist only in this area. Why? Because same pattern of the mask I can get on the photoresist. After this I have to, so actually we missed one step, not exactly missed one step, I have not drawn correctly. We have this metal here, you see here, this one is your metal for heater, right. So, we have here your metal for heater and here we have your photoresist, this is same pattern which we had on the mask. So, we have your photoresist, we have your metal for heater, Now I will post bake the wafer, this chip, this wafer, I will post bake this wafer, right, and then I will dip this wafer, post bake is done at 120 degree, you know, and I will dip this wafer in the etchant, ETCHANT etchant for heat, for the metal that is used for heater, that is the metal which is used for heater. I will dip this wafer into this etchant. What will happen if I do that? If I do that, then I will have metal protected only beneath the photoresist, correct, only beneath the photoresist, rest of the metal was not protected, it will get etched, Now, I will dip this wafer, in acetone, If I dip the wafer in acetone, what will happen is a stripper for photoresist, that means my photoresist will go, and what I have? I have oxidized silicon substrate with a heater. On this I will deposit or I will grow insulator, alright. This is my second mask, and then I will have I can protect the contact area somewhere, I cannot grow insulator on that area. So, that is fine. On this insulator, we can deposit another metal, okay. On insulator we are depositing another metal, this metal is for interdigitated electrodes. After depositing this metal, we will spin coat, once again we have to do the same process, we will spin coat photoresist. Then what you have to do? Pre-bake at 90 degree. Then what you have to do? Load the mask, This mask is for patterning the metal for interdigitated electrodes, mask for, this is my bright field mask for patterning the interdigitated electrodes, right. After this what we will do? You will expose using UV. When you expose using UV, after that you have to unload the mask. When you unload the mask, then what you have to do? You have to dip the wafer in photoresist developer. So, when you dip the wafer in photoresist developer, what you get? You get photoresist saved in the area which were not exposed. This is photoresist which is saved in the area which was not exposed. That is, it is retaining the same pattern with the mask head. After this I had to dip this wafer in the etchant for metal which is used for interdigitated electrodes. After this we have to etch this wafer, right, or dip this wafer in the metal etchant which is used for interdigitated electrodes. So, we will dip this wafer in the etchant that can etch the metal which is used for interdigitated electrodes. When we dip this wafer, what we will get? The metal below the photoresist would be protected. After that we will dip this wafer in acetone. When we dip this wafer in acetone, what we get? We get photoresist is stripped off. When photoresist is stripped off, you have interdigitated electrodes. Now, what you have? You have heater, right. You do not have just metal, you have actual heater, you have insulator, you have interdigitated electrodes. On this interdigitated electrodes, we can deposit material which is your semiconducting oxide or metal oxide semiconductor, such as ZNO, right. Now, after this you have the sensor ready, but the silicon is thick. So, you have to reduce the size of silicon. So, for that you have to etch the wafer, and when you dip this wafer, you can do two things. One is called dry etching, we will see, another is called wet etching. If you use dry etching, then you can etch the wafer by protecting the front area. You can put this wafer in the dry etchant, and what you will see is it will keep on etching until the thickness that you require. This is dry etching, right. This is a protection, this is a front area we are protection, okay. Or if you use wet etching for silicon, this is we are etching silicon, right. Then what you will have? If I have wet etching, then I have a diaphragm, this is called a diaphragm, 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 alright, diaphragm. So, you can have this thin diaphragm of the sensor, and then you can remove the front area protection thing. You got it? You got it? So, it is a lot of process. So, if I do not do this backside etching, then it is easy. If I do not do this backside etching, then my sensor becomes extremely easy, because I had to just keep on growing the heater, then I had to grow the oxide, on that interdigitated electrodes, on that I had to grow the sensing layer, that is it. But the power consumption is high, that is why I have to etch the wafer from backside, So, when you do this, how your sensor looks like? You see, this is a cross sectional or a blown up diagram, where you see there is a diaphragm, right, and you can see there are interdigitated electrodes, and there is a heater, which is nickel. We have used nickel as micro heater, right, you can see, and this micro heater is all the way here, and in center there are interdigitated electrodes, on which we have grown zinc oxide nanowires. How zinc oxide nanowire looks like? You can see the SEM image right over here, zinc oxide nanowire. So, when you actually operate, this is how the heater is operating. You can see this yellow color, this one, right, this heater is on, these are connection to the interdigitated electrodes, this is connection to the interdigitated electrodes, and this one is your zinc oxide sensing layer. You can see here in gas sensitive ZNO nanowires, right. Now, this is another cross section, is the same thing, right, just the material is different, and you can see that you can also perform the COMSOL simulation to understand what is the heating characteristics of the micro heater that you have designed on this oxidized silicon substrate, right. So, the idea is not to confuse you with why we have to use gas sensor or how this ZNO nanowires are created. We do not care. What we care is how you can grow, or how you can process, or how you can fabricate, right, a device, that is the idea, how you can fabricate a device. And for fabricating a device, you should know the process flow, right. So, if you quickly see this particular slide, you will understand what I was talking about, right. You start with double side polished silicon wafer, then you grow 1 micron oxide, right, easy, then you grow 60 nanometer metal here, you can see metal is here, then you open the window, that means you grow the metal, you do the lithography, then create a window, this SiO2 that can be etched, right, that can be etched by using BHF. Now, in the front side you can have the nickel micro heater. On nickel micro heater you can have electrodes. This is just an electrode, right, there is no heater here, that is why. So, but actually there is a nickel deposition. So, this is a heater, right. So, after the heater, after this particular process, we have this nickel micro heater, on which there is a insulator, on which there are interdigitated electrodes, on which there is a sensing layer. This is what it is here, So, we have double side polysilicon, then we have 1 micron SiO2, then we have 600 nanometer aluminum backside, then we have front side 300 nanometer nickel deposition, we pattern it, then we grow the oxide, and then on that oxide we grow the interdigitated electrodes, and then on that we have zinc pattern by a technique called lift off or lithography. Then on the back side we remove this oxide with the help of buffer hydrofluoric acid, we etch the wafer, right, and when you do this one you can have the sensor, This is a process flow for fabricating a sensor, Now, until now we have seen two process flow. One is the process flow that is used for one is a process flow that is used for creating interdigitated electrodes in SU8 well. Second is the process flow for understanding how you can fabricate a sensor, how you can fabricate a gas sensor, right. Two process flows we have seen. So, this is enough for us to understand when we look at the MOSFET fabrication, when you look at the MOSFET fabrication. So, in the next class let us quickly see what are the process, what are the techniques that we can use, what are the techniques that we can use to fabricate or to fabricate the MOSFET. So, the techniques that we will be using or techniques that we will be understanding would be oxidation, it would be oxidation, thermal oxidation, and then we will see how metals are deposited, then we have to see how the lithography is done, and then we will see what are the etching techniques, then we will see how the MOSFET is fabricated, and that particular set of experiments will help us to understand how we can fabricate a MOSFET. Once you are able to understand how you can fabricate a MOSFET, then you can fabricate lot of devices. So, the role of this particular exercise, understanding how interdigitated electrodes are fabricated within a SU8 well or a sensor that is fabricated on the oxidized silicon wafer, or if you want to create a diaphragm or you want to create a heater, on that heater we have insulator, on insulator we have interdigitated electrodes, on interdigitated electrodes we have sensing material which is your metal oxide semiconductor materials which are like zinc oxide, tin oxide, indium oxide, and so on and so forth. All this exercise that we are doing, I am repeating it 10 times so that you understand the process. The process is extremely simple. When we go to the MOSFET, then you will understand why or which techniques we have used to grow the oxide layer on silicon, which techniques we have used to etch the silicon, which techniques we have used to open the window, right, because we had to understand how source and drain are diffused in the MOSFET. So, to understand how source and drain are diffused in the MOSFET, these processes that we are discussing today will be extremely useful. Alright. So, I will see you in the next class, and till then learn again, look at the video. Microfabrication, it looks very simple when I am explaining you on the screen, but in reality it is difficult to understand. But once you understand, it is very easy to understand lot of process flows, lot of recipes. Alright. So, I hope that you have understood something from today's lecture, and you read it, you understand further, and if you have any questions you can ask me questions when we reach to the lecture where I am explaining you the MOSFET, because at that particular point you can go back and correlate your things and then you ask me a question. Here you may have lot of questions, but let you wait, have some patience until we reach to the lecture where I explain you how you can fabricate a MOSFET. Alright. So, I will see you in the next class. Till then, you take care, have a nice day, bye.